Uh, Hello, everyone. We are very excited to welcome Chenghao Li, who's a PhD student at ETH AI Center, co-advised by Professor Michael Harter and Andrea Krauss. His research explores general-purpose learning algorithm for automatic agents with special focus on achieving agile and natural behaviors of the robots. So I'm very excited to welcome Chenghao here, and then I will give the time to Chenghao.
Yeah, thanks a lot. Thanks a lot, Hawking. And thank you, Maltak, for inviting. I feel very honored to talk about my journey in the field of learning from demonstrations. So, a brief introduction of myself. I'm Chun Hao. I'm finishing my second year of my PhD at ETH Zurich at the ETH Center. I'm co-supervised by Professor Michael Hutter in Robotics System Lab and Professor Andres Causa at Learning and Adaptive System Group. Yeah. So the reason I want to talk about this is, nowadays getting very popular. Well, now that everyone is working on a humanoid, well, training purely using RL reward doesn't suffice anymore. So we always have some human reference data out there, and we try to learn from those data. And well, if you've never done that before, and if you want to start doing that, there seems to be 10 different ways of doing that. How to do that? So I want to kind of give a guideline to people who are kind of new in this field, also like people who want to see different things, good and bads about different methods. You know, to, um, to share some insights from my own journey playing with existing methods. Yeah, great. So the title goes "Learning from Demonstrations from Generative Adversarial Training into Representation Learning." So I'm going to talk about these two parts later. Um, yeah, first I want to define our scope. So I'm calling this learning from demonstrations or motion priors. By demonstrations or motion priors or reference, whatever, I really mean offline state-based reference data. So we don't have actions. We don't have expert actions. And all we're doing is trying to convert it to some reward signal that can be used during RL training. So after introducing this, so we're not really talking about imitation learning, which people nowadays normally refer to behavior cloning, which have direct access to expert actions. For example, well, a lot of people do in manipulation. You have some human expert, demonstrator, operator operating the machine, and you record the state action pairs of the machine. You get this expert state action, and then you train a policy trying to imitate that using supervised learning. So we're not really talking about that. So, this also rules out all these diffusion policies, doing like paper folding, laundry folding, and also robotic foundation models where people, just pick up something and the expert actions are normally just the end effector positions or pose. Yeah. So we're not talking about those. Um, yeah, great. So by learning from demonstrations, we want to convert offline state-based reference data to some reward signal. In other words, you can think of this as some inverse RL. We try to learn, or not necessarily learn, we try to construct some reward signal from this offline data set to guide our RL training. So why we're doing that? When I read the papers, many people kind of focus on the first like biomimetic reasons. We want the motions to be agile, to be natural, want the motion to save energy. So we have these reference motions to guide us to achieve this. But more importantly, I see the larger benefit of using demonstrations in learning itself. Um, Nowadays people work on humanoids, right? And before, when people work on quadrupeds, why are not people? Well, why were people not using reverse motion that much? And that's because we have nowadays with the humanoids, for example, with a much larger sensory motor space or much larger action space where we have to do actions. So imagine you want a humanoid to walk, and of course all the arms are really not useful, right? All the joints on the arms are not useful. So it's very hard to regularize the arm motions when it has nothing to do with a task. So in this increased sensory motor space, having reference demonstration can really guide us or guide the policy to explore meaningfully in the action space. And this will save us a lot of time. So your agent is not exploring in a enormously large action space doing something that's completely relevant to the task. And this really leads to efficient training of the policy. So yeah, as I said before, all about learning from demonstration is trying to extract the reward signal from the reference motion by using some algorithm. Well, yeah, this is a very simple framework. On the left, we have the reference. I'm going to call it reference for now. And on the right, we have this RL loop where the policy outputs some actions, which normally are the joint desired positions, and sent to the robot is going to move and send it back to the policy. Yeah. So the easiest thing we can solve this, where we can think of this is, well, we have some reference motion, right? It's a sequence of frames, a sequence of states. And the easiest thing we can think of is, well, you just calculate the distance between the current state and the state in the reference motion. You get the L2 distance and use that as a reward, right? And this is basically a very initial idea of deep mimic. This is kind of initial work in this field. But when you think about this, actually things can go wrong if you have more motions. Because the reference motion is like a sequence of states, and you have to determine which frame I'm comparing my current motion with. So you do need some notation of the current time index or phase. And when you have more motions, it's a bit hard to manage because how are you going to align different phases of different time index of different motions? How do you transit from one motion to another? It's not very clear, right? You have motion 1, 2, 3, but they are not encoded in a way that reflects their semantic meaning. So let's leave that aside. We'll come back to this later. I call it feature-based learning methods or feature-based imitation. So one straightforward alternative that many people can think of is GAN-based method. By the way, we're summarizing these two mainstream lines of method in our paper, feature-based versus GAN-based learning for demonstrations. You can definitely look it up. These are kind of summarizing all the current existing algorithms out there, from the earliest deep mimic to the latest, maybe GMT, deep mimic, all this kind of beyond mimic, this kind of stuff. So it's really we try to write a survey paper and try to include everything, and this hopefully can provide a good guideline for you. Yeah, so GAN-based method, what does it mean? So this algorithm block here is simply a discriminator. And the only job the discriminator is trying to do is to distinguish the motions in your reference data set from the motions that you actually generate. And when the discriminator cannot distinguish these motions anymore, it means your policy is able to generate the motions that are very similar to the reference. So that's great. And the key advantage here is, since the discriminator is comparing two distributions, it's not matching frame by frames as we talked about before. So this really scales to larger data set with different kind of motions. With you don't have to really deal with the synchronization, the motion embedding, etc. But it comes with problems also. And for anyone who has played with GAN or generative adversarial training, I wouldn't imagine you would say that's a pleasant thing to play with, because of the problems of GAN. Like first thing I would call it discriminator saturation, which is, imagine your reference motion is something like very, very agile, very hard, like doing backflip. And if you train everything from scratch, right, at the beginning, while your reference motion is doing a backflip already, your robot cannot even stand. So it makes it very easy for the discriminator to distinguish, this transition is from the reference motion and this transition is from the robot, right? So when the discriminator is very strong, the reward signal it generates that the policy receives is really not informative. The policy doesn't, see a way to conceive the discriminator anymore. So the policy doesn't learn anything. And this is the discriminator saturation problem we're talking about. The second thing is kind of more famous, the mode collapse, which means, well, in reference motion, if there are, say, 10 motions that can help you finish the current task, and there's no reason for the discriminator or for the policy to pick a second one if one of them can already do the task, because the discriminator cannot, it just cannot distinguish already. So we have a loss of diversity on the policy side if we have multiple different motions in a reference motion that can achieve the same thing. So the policy is not able to recover all different modes in reference motion. So for the initial works I'm going to mention, we're dealing with these two challenges especially. Well, when you have very clean reference motions, that's clean, well retargeted, very dynamic, consistent motions, things are a little bit easier. And of course, you can pick whatever methods you want to do. And here, when we talk about these potential failure cases for GAN-based methods, we tend to look at more realistic setups where we have the motions being rough, incomplete, misaligned, suboptimal, noisy, unlabeled. I'm gonna talk about what they are later. So this corresponds to the three works I'm gonna briefly mention. And first thing, we propose something called Wasserstein-based paper imitation, or Wasabi, to deal with that. Let me motivate you. So imagine now I have this quadruped robots, and it can do something in this gray region. Oh, let me maybe try to use a marker. Yeah, in this gray region. And now in the demonstration, it's something crazy, like a backflip. Of course, this will result in the discriminator saturation problem, as we talk about, because initially, while your policy cannot do anything, the discriminator already becomes too strong, right? So if we use this GAN-based method or like eternally adversarial motion priors in this field, we have exactly this problem, discriminator being too strong, the policy doesn't see a chance to improve. So what we propose here is also very simple because like traditionally people use LS GAN or least square GAN in this GAN formulation of motion imitation, where this discriminator is simply a classifier. So it just tried to classify everything, the transition from the policy to -1 and the transition from the reference to +1. And that's it. We're kind of, classifying it's a binary classification, right? But it's bad in the sense that it tends to get very strong already at the beginning when you try to absorb these or anchor these two prediction to these 2 points. So our modification is very simple. We try to use a Wasserstein implementation. So what the Wasserstein implementation is doing is not like saying, oh, please regress everything to -1 here or regress everything to +1 here. Instead of doing that, just try to push the predictions of the transitions from reference far away from the transition from the policy. So, it's not anchoring to 2 points, but you're trying to push them far away from each other. So you can see there's really no notation of saturation here. So maybe your discriminator is very strong, they're very far away, but the policy can always get a chance to see, oh, actually I can reduce this distance a little bit. And it is this tiny little, nuanced or a little change that the policy can see. Well, there's a hope that I can change to make my motion a little bit closer to the reference motion. That's kind of the logic behind. So these are experiments to give them an example. We flipped our robot with our hand. So when I say this motion is rough because handheld, so really, we don't really necessarily obey any physical laws. And it's partial because, when you flip the robots, the joints are nearly it's useless. So you only have very partial information about the base. So in this case, we deployed Wasabi. We trained Wasabi in a simulation and deployed back on the hardware. And it is exactly because of the Wasserstein formulation of discriminator that makes it possible for the policy to pick up tiny changes that can improve the policy performance to get a little bit closer to the reference motion. And here is a slow-mo. You can see all these joints, like lag motions, they are figured out by RL itself. We don't have any guidance on the lags. Yeah, that's it. So what we're saying here with the Wasserstein formulation, you can mitigate the problem of the discriminator being saturated.
I guess I will jump in to ask a few questions, and then if other can also ask questions.
Definitely.
It's a very complex. Can you give me a little bit of intuition of why the Wasa time why how why this work at all
Yeah.
yeah.
Yeah. So we are comparing Wasserstein or double gun with Alice gun, which is a least square gun. It's all about changing the loss function for the discriminator. So in the traditional setup, it's like binary cross entropy loss, binary cross entropy loss. And in Wasserstein formulation, this is more like unsupervised in a way. that you don't have targets. You just kind of push things far away from each other. This is the loss we use to train the discriminator. So to interpret the D is for the discriminator, and we are just saying please push them away, please push the prediction of the reference away from the prediction of the policy. And this way, we have a better figures in our paper. You'll see the reward landscape learned by the Wasserstein formulation has a very informative scale, such that like even far away in some states that are far away from the reference motion, you can still get the signal of knowing how to get to the reference motion. And this compares to in LSCAN, where close to the reference motion, you have very informative reward, but far away, you don't really know where to go. Yeah.
So it's a little bit more sparse, right? Like in terms of the
Exactly. LSCAN is more sparse, and double gun is more more informative, more dense.
and then the sparse is the better in this case.
Sparse is not better because at the beginning of the training, the policy cannot do anything, so we're really far away from the reference motion. So being sparse means we don't get the signal.
Oh, I see. I see.
Yeah.
Okay. Great, great. Thanks.
Yeah. Cool.
Like anyone have other question can jump in. Like
Sure. Yeah.
yeah. But
Yeah, you can just stop me at any time. Like we're gonna talk about one break after another, so like, you can just ask questions when everyone is on the same page. Yeah. If not, I can move forward. So if you're in a field, a lot of the motions, the reference motions, but now we're talking about humanoid, right? Human motions, there are mocap data, and they're recorded in mocap system under mocap system, and normally they're on flat terrain. Studio, it's normally on flat terrain, but in leg locomotion, we care a lot about, well, since it's legged, right, and we're not wheeled platform, so we care about a lot about terrain traversability. So let's say going upstairs and going on pillars, whatever, stepping stones. But this is bad because we don't have exact reference motion for these tasks. We only have the, say, walking on flat terrains. How do we leverage the information there? And again, this is a similar problem of the discriminant saturation because what the policy is trying to do is kind of different from what the reference motion has, right? So it's kind of divergent. And then again, you have a very strong discriminator, and that's bad. So in this case, it's a very simple idea. It's called, we introduced a constraint style mimicry or a constant mimic with just accepted curl. So you may talk with Kehan. I think Kehan is also here during curl. The idea is very simple. A desired task, we want to go upstairs, but in our demonstration, we only have flat terrain walking. How can we learn that? It's a very simple idea. We want to maximize the value function of the style only after our task condition is fulfilled, which means, well, now, for example, I'm tracking a velocity, and I will ignore my reference for now, but I'm trying to track the velocity only after, say, 90% I'm happy. Then I start to introduce my reward or my style reward in to, now please do something similar to the reference motion. So this way, I have the guarantee that my task fulfillment is always 90%. And when you cannot do the task, please do the task. When you can do the task, please try to learn a little bit style. That's it. So we formulate this as a constraint MDP or CMDP, and with some Lagrangian method, we can approximate to using RL. And some results we have, this is the task only. So this has no reference motion. We can work upstairs, not as natural. And AMP is the one we talked about before. If I have some small imitation reward for AMP, it really doesn't change too much. I have a very large AMP, since it's the reference motions are on flat terrain, right? So if you have very large imitation reward, it doesn't make you move forward, because once you move forward, you're going to produce something that is different from reference motion. And in our case, with the balanced or automatically balanced constraint fulfillment, you can see we have much better, say, well-aligned motion while traversing on rough terrain. We can learn from the flat terrain references. Also, we validated on some stepping stones. Again, task only is kind of going, but on a wrong direction. AMP small is very similar. AMP large doesn't move at all. And in const mimic, you can see it really tries to do the task while mimicking the reference motion on flat terrain. Great. That's our second work on GAN-based method. And third one, we want to try to deal with noisy unlabeled data set. Let me introduce cooperative adversarial self-supervised skill imitation, or CASI, if I may call it. Some motivation behind. Well, imagine you have some, say, human doing all this reference motion. It's very easy to tell the human, please walk now, or please run now, right? You have this label for what your human is doing. But imagine now you have some cat, and you want to record motion from a cat. It's not able to tell the cat, please walk only, or jump only, or do a specific motion only. What you can do is record a long sequence motion, and then after that you inspect what the motion is. Then you can segment it into different categories of motions, right? So what you get here is a kind of demonstration mixture. It contains all different kinds of motions. Once this demonstration is getting large, like you have more data coming in, then it's not possible for the human to really annotate this motion anymore, to segment this motion. Plus, motion is not like pictures. Motion is always a time sequence. So it's very hard to do that. So what we're trying to say here, like given this mixture of demonstrations, can we directly train a policy out of it that can pick up the individual motions out of this same mixture of motions? That's our idea. Without knowing their labels or their segment. It's just throwing everything, and let's try to extract, say, 8 motions out of it. The idea is very simple. Let's focus on the right side. Imagine this gray area is your say motion space. When you say, oh, let's try to extract one motion out of it, you can get this 0, 0, which is the motion embedding, and you can get a second one. But what we want to introduce here is, because GAN has this intrinsic problem of mode collapse, what you get from Z1 will be very close to Z0. You may not even distinguish them because, again, the policy is not able to recover a second type of motions, since the first one can be already enough to confuse the discriminator. Then you can introduce some additional force to push them separate away from each other. And this, we use the mutual information maximization. Here, let's write out the mutual information between this motion embedding Z and the motion transition. So when we write it out, it can be described as the entropy of the transition, which describes diversity, and the entropy of the transition when you condition on this motion embedding. And if you add a negative sign there, then this becomes predictability. So, entropy describes the uncertainty, right? We want to maximize mutual information, means we want to maximize the diversity. I want this transition to be as different, as diverse as possible. But when conditional on my latent encoding, I want them to be as determined as possible. And this way, we're really saying, oh, please do the motion such that, or encode the motion such that I really increase my discriminability of the motion. Of course, you can convert this to some reward. And on the right side, we have this additional force based on mutual information to push this encoding away from each other. When we introduce more motions, we have kind of rather clean separated motions, each corresponding to some mode. And this whole process is unsupervised. So you cannot really control which motions eventually you want to get. So what you can say here is, well, please give me 5 motions and make them as different as possible out of this whole mixture of demonstrations. And again, this is our experiment. We have this mixture of demonstrations of the robot doing different gaits. You can see some wavy motion and with different heights, different forward speed, some jumping. Yeah. And again, our data set is unlabeled. We don't know what are the motions in there, and it's mixed. We don't know how many of them are there. And let's say now please track So 6 motions. So this is the motion we extracted. So this is a single policy. When you condition on this different z's, you can have very distinct motion behaviors from this single mixture data set. Yeah, that's all about Cassie. Great. Is that perfect time point for questions? Yeah.
Yeah, like I would like to jump in. So
Yep.
all the latent like the latent skills that you find, like what they mean is that you later label them, right? Like basically, like the
Exactly.
walk, the crawl, the still, like it's like you look at the behavior and then you say, oh, like that's
Yeah, exactly. Because this whole process unsupervised, you can only do that later after extract, then you give them the meaning. Yeah. And every seed, this will give you completely like different 5 motions in our case.
like is there something interesting between the transition of the latency? I mean,
Mhm.
like when you push this distribution away, for example, Z0 to Z3, like what's between them, right? Like
Yeah.
if yeah.
This is a very nice question. We have this information in our paper. What we realize is, for example, let's condition our policy not on Z0 or Z3, but something in between. Then we have a very nice interpolation of the motions of, like, for example, here is kind of walking plus jumping with a low base height. So this interpolation did happen. So what we're trying to form here is a nice latent space or latent encoding of all these transitions, and the interpolation in between really reflects some mixture of these individual modes. Yeah. Uh, I didn't put the picture here, but yeah, we do have a section in the paper dedicated in this. Thanks for the question. Great. I guess I'll just move forward. Yeah, so this is about this GAN-based method. You can see like GAN has some problems. We propose these solutions to solve this problem. Um, but let's think back. The initial motivation of introducing GAN is because we cannot easily deal with, different kind of motion, diverse motion, large motion data set. Because, you have to do the synchronization, you have to do motion encoding in a way such that it's meaningful. Um, but let's jump back. What if we can already do something in trying to improve the embedding of the motions? So here we're talking about the second stream, which is feature-based method. So we're saying before, well, instead of using this discriminator, I'm computing my imitation reward basically based on the distance between the target state and my current state. Yeah. But again, we still have to solve the problem of synchronization and motion embedding. So what people normally do is, well, you have to inform the policy in a way which motion you're tracking, right? You have, imagine you have 10 different motions. You have to tell the policy this is motion 1, 2, 3, 4, 5. And we can encode the motion in this embedding phase, embedding space, which is theta in our case. You condition the policy on this. And this can be either, a latent embedding, or it can be the exact frame you're tracking. That's kind of very popular these days in the latest works. Yeah, but there are challenges. First is, well, we don't want to just simply use any embedding space. We want this space to be as informative as possible. For example, if we have, say, standing motion, running motion, and jumping motion, of course, we want embedding between stand and run to be close than jumping, because jumping sounds is very different. Like, we want to have an informative, well-structured latent space. And the reason is the policy, when conditioned on this space, can generalize better. And also another thing, another challenge that feature-based methods have is this imitation is based on frame-by-frame condition, frame-by-frame comparison. It's not as flexible as the GAN-based method, which are based on distribution comparison. So it's a bit of a hard to introduce additional, say, completely different tasks when you are in the setup. So we're going to deal with that later. So again, we introduce 3 works when these reference motions are poor, inefficient, and flexible, over constraining, or inefficient sparse. And I'm going to talk about this. So first thing, Fourier latent dynamics. Let me again motivate you. So imagine now you have this nice data set of a human doing different things. This, for example, is kind of a stepping in place, and you have some kind of striding motion. And you have this rather sparse reference motions because when you record data, normally you can get like hundreds. No, I don't think you can even get hundreds of motions. But imagine I have these two motions already here, but I don't want to learn only these two motions. I want to learn all the motions in between, but I don't have the motions in between recorded. How can I build a space such that I can do meaningful interpolation, that I can recover something in between? This is like running motion. And what we introduce here is something very simple. Well, it looks complicated, but this is nothing but a autoencoder. It's something called a periodic autoencoder. So if you look at this is the input. Input is the state transitions, like state, state, state. We have a segmented state. We encode it in some latent space. We reconstruct it and decode it to the original space, right? This is the autoencoder. So what's special here is this Fourier transform here. So after we get the latent embedding, after a convolution layer, we perform a Fourier transform on this latent embedding to extract the latent frequency, amplitude, and offset of this frequency of the latent embedding. So here on the left, this is the input, and this is the latent channels. And then after a Fourier transform, so here we are extracting them into 8 channels. So 8 channels each have different frequency, amplitude, and offset. And then we have assumption that, well, if these motions are kind of periodic, because, well, locomotion motions are always periodic. Just imagine, even if you are hopping with your single leg, that's also periodic. It's very hard to get aperiodic motions. So let's think about like locally periodic motions, since this defines your trajectory or segment length. We have very high confidence that we can recover the original motion by using sinusoidal reconstruction. So here, what we do is, well, based on the latent frequency, amplitude, offset, and also some phase variable, we can reconstruct latent space using only sinusoidal functions. So you can compare this previous, like original latent space versus the reconstructed latent space. They are somehow different, but most of them are like essentially the same. After that, we deconvolute it and get the reconstructed segment, and we compute the loss on just reconstruction loss. And this is a periodic autoencoder. It's not our contribution. It exists before by Sopistaka. After we plug in our motion, we realize actually when we look at the frequency, amplitude, and offset domain, actually they are not changing that much. So that really reflects our argument that locomotion motions are locally periodic. And the only changing part is this frequency, which is acting as a time index. It's kind of advancing periodically. So what we propose, the new thing we say is, given this nice structure of our motions, can we enforce this invariance in the latent parameterization space in the training of the periodic autoencoder? So on the left side, this is exactly the same as before. We reconstruct the reference, the original motion, and calculate reconstruction loss L0. But instead of doing this per step, we can also propagate our motions forward by using some latent dynamics where theta, again, this is now I'm calling them theta, this frequency, amplitude, and offset in the latent space. I assume they don't change over time in my motion period, my short motion period. So theta t plus 1 equals to theta t. And the only changing part is the phase variable. So now you can say we're trying to decouple the motion from, it's a time domain thing, into something that is changing over time and something is invariant over time. So more like frequency that is invariant over time and the time index is changing over time. Yeah, so after doing that, we just have assumption theta t equals theta t plus 1, and this phase t plus 1 can be calculated by advancing the phase variable. So we can reconstruct doing the same thing, and we calculate reconstruction loss on the next step. Of course, you can do it for future steps too. So here, we are like implicitly telling the periodic encoder to encode the motion such that the theta encodes the invariant motions, while the phi, which is the phase, encodes the time varying ones. Yeah. So let me give you a schematic view of what we mean. If you think about theta, this like frequency domain parameterization, we call it quasi-constant parameterization, as some radius, and this phi, the phase, as some angle around central point. So while we're traversing on a motion, we're inducing this rain. And well, if we have different motions, we have different rains of different radii. And if we plot all the motions in a data set M, these are going to be how it looks like. So we compared our FLD embedding with all different kind of other embeddings. Like original embedding, you can see the motion is, it's kind of periodic, but they're kind of clustered together. VAE is nicer embedding in the space, but again, the time is coupled with motion. And PAE, without this propagated latent dynamics, quasi-periodic, quasi-constant assumption, then you see a nicer view. But FLD, this is much nicer latent space. And what's really good about this is once you decouple time from the motion, high-level description, whether this motion is walking or standing or jumping, then you really hugely reduce the number of parameters you need to describe this motion. Because again, the only changing part is the phase, is the time. And what you only need to do is to keep the number of this frequency amplitude offset. And that's fixed. That doesn't change with your length of the motion. So here C is the latent channel, which in our case is 8. So for C, because there's time, there's frequency, amplitude, offset, and phase. So there are like 32 parameters you need per motion. And this is decoupled from the original motion. In our case, that's like 100 steps, and the S is I think 40, so that's like 4,000 parameters. So what we eventually get is very compact space that has a very nice structure that has this decoupling from the time invariant part and time varying part. So on that part, we're only talking about motion representation. So we take in all the kinematics, we output all the kinematics. So there's no physics, no dynamics going on. So what we do after having this nice motion encoder and decoder is to train the RL policy to track them, right? So every time we sample a theta, again, this time invariant frequency domain parameter theta, we sample some phase, initial phase, then we condition the policy on this nice parameterization space, and we calculate the reward. Well, definitely after reconstructing the motion, we just calculate reward frame by frame. So this really addressed the problem, as we said before, feature-based methods are not really good at motion representation or motion like synchronization, right? So this is really provide us with a solution of achieving so. So during policy training, at the beginning of each episode, we just sample a theta, we sample a phi, but only after that, you can keep the high-level description of the motion the same throughout the trajectory, throughout the episode, while advancing the phase forward. So this way, you're staying on the same motion, but you're learning, the subsequent frames of the same motion. And during inference time, what you can do is you have some user inputting this motion, you can encode it, you can get this latent space in the parameter, the frequency domain parameterization, and also in the time domain phase parameterization. And the good thing about this is, well, you don't need user input all the time, because even if you don't have that, by keeping on the same motion, this high-level description theta, while you're propagating your phase, you're actually doing this thing periodically, like again and again. So you're free from inputting reference motions. So a good illustration here is, imagine we start from here, and now we have user input giving us, oh, you should do this, 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 all these blue dots. And we can define, because this is an autoencoder, right? We can define a region where we are confident about the training distribution. So we have this shaded region, and outside we can easily detect anomalies by calculating the same loss. We can define a threshold. And for example, this user input and this user input is kind of outside of the confidence region. Then we just don't track them. And instead, we can fall back to the motions we know about by staying on the same frequency domain parameterization, but advancing the phase. So the eventual motion we'll get is this one. And again, here you can see the user input doesn't have to be periodic. It can be literally anything. But if you are if you're diverting too far away from your training data, or this safety mechanism or fallback mechanism will always drag you back to the safe motions that the encoder and decoder are trained on. So here are some demonstrations. We're tracking this target. And whenever this frame is graying, it means the motion has never been seen before. So for example, this kicking motion is not seen before, so we're not tracking it because of this fallback mechanism. And of course, you don't need to provide input all the time. You can just leave it doing the same thing. And now it's tracking. Now it's tracking this motion. And now it's not tracking this dancing. And here I have the latent manifolds going nicely in this circle. If we want to compare with our fallback mechanism and without, for example, here you can see it's kind of already stomping if we don't, if this motion is not in our training data set. So basically on the left side is track every motion that the user provides. On the right side is, well, be smart and use this filter of motions. Yeah. And if you still remember earlier, I motivated this work of, I have the motion recording, like motion data set for motion 1 and motion 3. How can I get motion 2 in between? So what we're saying here, this data, this parameterization space in frequency domain is a very nice one that you can do even linear interpolation in to get a very nice motion interpolation from here. So this really respects the spatial temporal relationships of the different motions here. For example, we have a theta step, a stepping in place motion. We have a striding motion. And now we want to say, let's try to do interpolation in this parameterization space of theta and decode it back to see how the motion looks like. And we can also do this during training, during policy training. So you can see this policy now is doing this linear interpolation transition to this motion, and now again doing linear interpolation, transiting to a different slower motion, and doing this linear interpolation again. And this policy is not trained on all these intermediate motions. It only have seen these anchor motions before. So what we're showing here is during inference time, you can even do this linear interpolation. So all this nice generalization comes only from the generalization of the policy and this motion embedding being good. And some other people applied also from the lab. They apply this on this this cute Aibo. It's a Sony product. FLD has a rather assumption of, well, you need to be locally periodic. But some motions are not locally periodic even. So we have some modifications. We call it deep Fourier mimic. If you can relate this work with deep mimic, so this is basically doing deep mimic, but we have an additional motion embedding, a nice one where you can, encode different kind of motions in, and we have the phase. Phase is the same, but now we have a much better embedding. And here we can see the transition where the deep mimic just do hard switches between motions, and deep Fourier mimic is doing nice motion. And here is again a frequency kind of diminishing. We can do transition very nicely, smoothly with our latent embedding. Yeah, that's the Fourier latent dynamics and deep Fourier mimic. Yeah, go ahead, Cody.
Yeah, I think I will jump in for one question.
Sure.
So like I think in most biological life, we have something called the central pattern generator in the spinal cord. Like if you
Yeah.
cut the spinal cord, like the cat can still walk in a periodic way. So basically, this would really assume that the periodicity of motions, right, or dynamics in everyday life. But human doesn't have that.
Mhm.
Like humans somehow sacrifice our central pattern generator. So like whenever the human spinal cord is cut, like you get paralyzed, right? Instead
Yeah.
of monkey and cats can still walk. And the assumption of why human give up this periodicity generator in the spinal cord is because human behavior are much more diverse, and especially of the hands. Like the I think like the theorists, they don't have evidence. They believe that we give that up because the manual dexterity, like the movement of our hands, are so aperiodic that we need to give up this periodic, like somehow generated in our spinal cord in order to have that. So like what do you see that view? I mean, like that directly go against to the quite exciting. Like it seems that periodic motions are something that we really want, but like is there a boundary when when the usage become really diverse and complex that we need to give that up in the biological life, like what
Yeah.
you shown to us? Yeah.
Yeah, definitely. Thanks a lot. I got this question a lot. It's a very good question. Like people are concerning, oh, you seems to have very strong assumption on periodicity. How does it generalize to, motions that are not very periodic? The first thing I want to say is the periodicity assumption is only applied during training. And during inference time, you can, have aperiodic motions. You can imagine like all these rings, right? When you have aperiodic motions, you can think about, oh, I'm jumping from one ring to another, but this can be continuous, right? So I'm gradually changing the dynamics, the radius of my ring too. So we kind of say, oh, in the original motion, we want this periodicity to get a very nice latent embedding, but it doesn't stop us from migrating in between. So that's kind of the first thing I would say to people who have this kind of question. And another thing is, oh, when preparing this data set, what if your data set is not periodic enough? So what you can do is you pass the Fourier transform already, like in the beginning, and there you can see this frequency change, right? Then you can cut this frequency, your motion transitions into pieces and make them like locally periodic. That's another way of how to train this. And third thing, if you really want to do something completely aperiodic that cannot be described by continuously changing from locally periodic motions, then um, what you can do also in this case is imagine you have this segment of motions and you can concatenate these motions. You can repeat the same motion, concatenate them. It doesn't have to start and end at the same place because everything we're doing here is training an encoder. It doesn't have to, it's only kinematics. It doesn't have to be dynamically feasible, etc. So you can manually construct this periodic patterns by repeating them, and then you get a nice embedding for that. So that's another way I see that this method can generalize to those aperiodic motion clips. But of course, the downside of this is um, imagine your motion is kind of long. It's aperiodic long enough such that you always have to, after you concatenate, your this window, this sliding window, has to cover at least one period for the Fourier transform to work well. So you have way more, say, computing effort for that. Yeah. But I totally agree with you. And in the next work, I'm going to talk about some more cases when you have not so much periodic assumptions. Yeah. Great. So that's the second thing, motion prior reimagine. All in the beginning, in the previous work, we have rather say periodic motions. Well, of course, you can extend them to a periodic settings by using techniques I was talking about. But what if we want to do something that is very different from what is in our data set? So in this work, we kind of use the same motivation. We want to do, for example, locomotion on rough terrain. In our data set, we have motions only on flat terrain. So very simple idea you can build like beside the const mimic using like constructing as with a constraint MDP problem is, well, we can train a low-level policy that works on flat terrain that is conditioned on this nice frequency domain parameters and which can generalize very well. And then I can have a high-level policy that's planned in this nice latent space to command my low-level policy to do the motions. But of course, this will also only work on flat terrain, but also have additional buffer, additional budget to modify directly the actions, like the joint actions. So here's the pipeline. We have, well, this is the motion embedding, the motion processing. We train a FLD as before, the frequency domain encoder and decoder. And then we have this low-level policy that can only work on flat terrain. And after that, we train a higher level policy that's kind of commands the latent embedding, the frequency domain parameters, the frequency, amplitude, and offset, but it's not enough. So we have an additional term to also, it's not in here yet. Here, we have a residual action output by the high-level policy to directly modify the behavior of the low-level policy, where the low-level policy is frozen at this high-level task training phase. And this way, we have you can think of the low-level policy as a library of motions. It's kind of a policy that when you condition on this latent embedding, you can do some motions already. So this is kind of a repertoire of motions. And when you train a high-level policy, this really reduces a lot of efforts of getting to learn how to walk, because that's kind of already handled by the low-level policy. And then while we do this kind of a typical policy distillation for better sim-to-error transfer, and here's the video showing that. So this is the low-level policy training. We have some motions for quadruped, and we train this low-level policy imitating these motions using the Fourier latent dynamics encoding. And during task training, we're able to train the high-level policy, which commands the low-level policy, with additional term residual action modifying the behavior of the low-level policy to generalize on rough terrains. And we also train on not only velocity tracking, locomotion task, and here is more local navigation, where we can say, oh, please navigate through this say cylinders and boxes to reach a goal. And eventually can deploy it on the hardware. Let's wait for a little bit. So we're showing this local navigation performance in simulation, and now in hardware on flat ground, you have you can clearly see a motion imitation here. Here we got the motion data from a real dog. You can see a real dog doesn't go backwards. So when you kind of turn, it has to turn jumping backwards. And on rough terrain, it generalized to terrain traversability. And this local obstacle avoidance, we have some humans standing there. It kind of learns to get around with the human, and also this corner, when you command some in position around the corner. Yeah, great. So last thing I want to very briefly talk about is we're talking about learning from demonstration, but what if we don't have demonstrations? That's a bit weird, right? So we want to learn from something that doesn't exist. So what's going to help us is generative models. So imagine you have no data to learn from. So we call no data imitation learning, or NIL. So what do we have? The motivation, again, is we want to learn from demonstrations, but we don't have them. What we can do is, well, we are training in simulator, right? So we can encode this frame of our simulator and put it as initial frame of a video generation model. So here I think we're using timeswarmer. So you can condition this video generation model on this initial frame and give task description of, for example, this humanoid should walk forward. And then this video generator will generate a time sequence of videos. And well, then you have demonstrations. You can use this demonstration, convert it to a reward, and train the policy. But of course, you don't compare them frame by frame because you already have a nice embedding via the timeswarmer. So you can directly compare L2 distance in this embedding space. And this gives you a meaningful information of the distance between motion frames. And we found also intersection of union, loss, or reward can also help. So what we do is we have this simulation frame, we like segment it, we got this humanoid walking, and we pass it through the video diffusion model. We got it. We got the sequence of generated videos, and we compute the L2 distance plus the intersection of the union and with some regularizations. And here's the video. These are generated demonstrations. You can see it's kind of working already pretty well with the current video models. We learn policy, well, it's not doing super well. Well, so this is like more like a graphics paper than a robot paper. So we're working on improving this performance. And also now the video generation model is getting way better. So it's um so we're improving this. Yeah, Paris, you have something?
Yeah, I wanted to ask, like this method is dependent on the quality of the video model, right? Of the video
Exactly.
generating model. How, what's sort of the most complex motion that you can get it to realistically make that still kind of looks good? Is it
Mhm.
walking? Is it running? Is it?
Yeah. So by walking, it's already very hard. So as you said, this is definitely our bottleneck of this video generation model. I think what we're using is also relatively like earlier models, such that we don't have very nice generated motions. But nowadays, since we have way better, stronger models, we hope we can generate better, not only better videos, but also better embeddings, such that this reward computation with L2 distance makes more sense. But also nowadays, since we have better, like large models, we don't even have to, you know, generate these videos and convert to the generate videos as some reference mode, as some reward. What we can do is we can input what the policy is doing as the video input to the model and directly tell the model the task. And the model should be able to give us a zero, like a reward function for that. That's also a hope, but again, like we're not training these art models or um, like our capabilities is kind of bottlenecked by this. But this is a fun project. We want to demonstrate, oh, you can learn from demonstrations without demonstrations. This is also possible and fun to do. Yeah, great. So this summarizes the feature-based method. So what we want to say here is we want to be able to scale to diverse motion data set. And while GAN-based method have all these problems of saturation, discriminator saturation, and motion collapse, let's check back on the feature-based method where we just compare frame by frames, but let's get a nice motion embedding such that we can generalize better when pause is conditioned on this space. And in total, I was presenting these 6 works. I hope it gives you some idea of what's kind of currently being done in the field. And like a quick summarize, we talk about GAN-based method, we talk about discriminator saturation, we can use Wasserstein formulation, constraint MDP to, to mitigate the problem that discriminator being too strong. And for mode collapse, we can have additional term um, based on mutual information to push our motion embeddings away from each other to make them as diverse as possible. The feature-based method, what really boils down is a nice representation where you can, for example, separate the time invariant ones from the time varying ones in the frequency domain, and or the video tokenizer where you have already a very good embedding there, you can directly compare the motions in that space. And again, we're talking about all these algorithms. Now we listed 6, but that's kind of from our group. If you are interested in all other what other people are doing, but also classified in these two kind of categories, including the most recent ones, definitely check this out, and I hope it can help. Great. That's it from my side. Let me know if you have any questions.
Yeah, let's open up for questions. Yeah. Thank you.
Thank you very much.
Anyone, just jump in. Anyone have any questions? I think there's one in the chat, like from Bruce. Like I will read it out. Um, can you explain at the end of the talk, what do you think is the biggest gap to transfer the learning algorithm from scene to real?
Mhm. Yeah, it's a nice question. And also, this is a point I normally mention to people when I'm advising them to present their work. So what we want to say here is like either method you're choosing is relatively, from my opinion, is relatively independent from the sim to real problem. So all these things can work very well in sim, but it doesn't guarantee your good performance in real. So you still need a lot of sim to real, like additional effort to do either domain randomization or all this adaptation method using distillation, teacher student training. So they're separate. I feel a lack of confidence arguing for one of the method that is especially good in transferring to real, because all these methods are trying to say whether they get nice motion embeddings, whether they learn motions very well, whether they can track them very well. So in my from the back of my mind, I don't see a direct connection to sim to real transfer. And also, a lot of people tend to argue, oh, with this method, our energy efficiency is way larger, our motion is way natural. Also, I think this is kind of a lack of, proof, because these methods only cares about how well you align with the reference motion. If your reference motion happen to be smoother or more energy efficient, then definitely your method has higher energy efficiency. But this is not guaranteed. If your reference motion is some like crazy motion like backflip, your method really doesn't translate to whether this method is better or not. Yeah, that's from my perspective. I don't think this method really have very direct effect in the sim-to-real transfer problem. Yeah. Hope it answers the question.
Thank you. Like, I guess Bruce want to follow up, or like any other people have any questions? Please feel free to jump in. If not, I have a few on the last part.
Sure.
Like, it's very interesting that you use video diffusion model. I think the first question I will ask is, like, do you see that as a like synthetic data generators, like which is like non-imitation, but essentially it's a data generator. And the second is that I was quite curious about how you say about, like, Sherry Yang, Elon Du, they've been doing some kind of the diffusion policies, and then the energy models, and then I think like Sherry Yang recently have a video planning, something like that policy, which like they use the video diffusion model and directly diffuse out actions, right? And then it worked pretty well in like in some kind of like manipulation tasks, not like locomotions. Uh, yeah. So how do you like regarding those works in terms of this, and then like what which is going to win the robotics run, and then and then also on the compute, how expensive is doing this, like compared to traditional like imitation learning? Yeah.
Mhm. Yeah. Yeah, that's a nice perspective. Um, so, but to me, like when we define the scope, we're really not say focusing on a problem where we have the action labels. So in our case, we don't really have the ability to diffuse the actions, since we don't even have the actions, like in either training or treating these models or not. So to me, this is like a video like generation model that is, just generating frame by frame. We don't have action labels. And of course, you can swap in all the state-of-the-art generation models conditioned on the initial frame. I think there are many of them out there, way better than what we use here. Yeah, from my point of view, I didn't see an overlap of different of these two ways you're talking about, like Elon or Sherry, um, on manipulation tasks.
I think Derek has a problem. Do you want to jump in and ask Derek? Are you there?
I can read it. I can read it out if
Yeah,
Derek.
I like, yeah, like if he cannot speak, I can just like how, like, he want to ask, like, how do you think about getting a general controller for whole body control, and where's the data, and what should be the framework, and what should be the interface on a high and low level? Yeah.
Yeah, yeah. This is a very nice question, and I think that's the main gist of this talk. I can fall back to the initial um, plot we show. Basically, it's this one, right? Here. Yeah. So many people now, what they do is, well, they don't have a very, well constructed or explicitly constructed embedding as what we just presented. What they do is they throw in a ton of different kind of motions in here, and of course they have either some encoder like variation out encoder, or directly feeding the frames into the policy. And sometimes they feed more than one frame, but all the future frames. So Well, if you have a large data set of different kind of motions, you hope the policy can generalize to the motions that you train on. Of course, all the motions in between, by condition on this kind of large embedding or sequence of frames. Um, this is also, is always a trade-off between data and structure. When you have enough data, I believe you can do that. Your policy will be very strong in tracking all different kind of motions. I think, like for instance, in GMT, they train really on a very large data set of motions, and condition on very long sequences. Um, but when I don't think it's possible, to collect all the motions that a human can generate to train our policy on. And plus, it's also hard to track these motions because maybe different motions need even different reward terms. That's something we didn't touch here. Um, so when this data is not enough, what we can always compensate or we can always mitigate the problem, lack of generalization, is adding structures in. So that really boils down to what we talk about today. How do we form a embedding space such that, well, without that many data, we can still generalize very well in this motion space. Yeah, that's kind of my take. Well, if you have data, definitely train on all of them if you can. If you don't have data, I think we can be smart about how to encode this data. How do we condition the policy on the structure such that the policy can be, general as well. Hope that answers the question.
Yeah, great.
Yeah.
Um,
Sorry, I missed. What should be the interface of high level and low level? Yeah, I think maybe Michael's here. A very nice work recently in the graphics community is Park, like where you have the low level tracking some motions that are using the direct frames as embeddings, and the high level can be a diffusion model trying to propose all these future frames. And that can be a good interface already if, again, your motion is diverse enough. You're very confident about the diffusion model can do, then you can do that. But yeah, we can always like in addition to that, we can always think of more structured latent space, and it facilitates the high level policy to be, we don't need a very strong high level policy to always generate frame by frame good motions, but be good enough to guide the low level policy in this nicely shaped latent space, such that the low level policy can also generalize better. Yeah. So I think it's kind of the same problem. Um, how do you kind of balance the data versus the structure, and how do you design an interface? Um,
yeah, I think Derek has a follow-up. How do you think about the recent days, so many very dynamic motion demo on G1? I guess he's talking about the Unity 3 G1. Yeah.
Yeah, I think it's cool. It's definitely cool, and I'm happy because I kind of started in this field relatively early. So at that point, we didn't have very good human hardware. So if we had access to human hardware, then it would be much more fun. So now, like, people seem to have better hardware, and now people are kind of realizing, reference motions can be really helpful in these cases. And yeah, I don't know how you feel about that, but when I feel that at the beginning, I think, oh, this is awesome. People are doing that eventually. But eventually, when you see all those demos of dancing, of this boxing, it's getting more and more. You'll see, oh, it's actually, it's nothing more on the algorithm level than what's kind of existing there. It's kind of bounded by the data set. Of course, you train on this motion, you have that motion played out. So it seems now on the locomotion skills, people are not showing, um, say, very impressive results on how they generalize, or definitely what we have, like in the research community, we have more work on that, how they generalize, how they can be scaled on, let's say, rough terrains, right? Now we have dancing motions on flat terrains everywhere. We have the boxing. We have some motions on flat terrain. So I see it's great that all the companies are doing that. Many people are working on that, and I see a great opportunity of either doing, trying to make it more generalizable, trying to scale it better, not only with the data, amount of data, but also with nice design of the structure, and try to apply it to other application scenarios than doing stuff on flat terrain. Yeah. So in short, the highly dynamic motions on G1, amazing. They're trained, I think most of them are trained with resonant motions. They're great. But this is also expected because these methods are designed for that. It would be nice to show something that is not expected, like, generalizing to something that's not trained on a dancing motion and on like flat terrain. Yeah. Thanks for the question.
Yeah. Yep. Anyone have any more question before we already like around 20 minutes or like more than what we schedule, but like anyone just jump in like before we close up. Great. Like I guess so I'm gonna stop recording now then